Professor Alu, Dr. Alu. The theta is in radians.
Usually it will be like.
Usually it should be in radians. Okay, so now we'll jump back to. We finished with the nozzle. Just look back a bit. We'll have to calculate the loss. So let's have a look there. Students, they did some simulation with the solid. I don't know how much it's worth. I don't like this thing. It's not made specially for this. It's very good in the designing, but I don't know how much is it doing well there. I didn't check. So they have checked. They made some stress analysis on the contraction, and so what was suspected that in that area where the inflection point of the nozzle, the stresses are the highest, and it shows also the expansion of the material. Of course, it is a bit exaggerated. It's not to that extent, but it just gave them a reason to believe that we need some fasteners, which we always see in such kind of nozzles. Here you see 5. I didn't like that there are only 5 frames. There is the inlet, the outlet, and then only 3 inside. But they were following up the contour, so I'm not worried that the void is maintained. Also the ribs, the longitudinal ribs were contoured with a numerical control machine, so it follows those. The loss in the contraction can be given by empirical formula, but you can work it out yourself as well. The first one is the empirical one. The head loss coefficient is it's 0.32 friction factor, average friction factor of the contraction, and the length and divided by the hydraulic diameter of the test section. Usually I don't like to work with this cookbook formula, so I was checking myself to see the pressure loss with the integral, the following formula, and in there, except the density, everything is a function of x. For every section you have its velocity, its diameter, so you can numerically integrate along the contraction. It's easy work. Even with Excel you can make it and get the pressure loss in the contraction.
So how to decide this length of this nozzle?
Length of nozzle usually, I mean, in our case, it's 1-to-1 of the larger dimension, the inlet. It's the dimension of the inlet, 1-to-1. And then you decide what is your contraction ratio. Okay, yeah.
First we need to decide contraction ratio, length.
Yeah, but in this case, on this fifth polynomial, curvature curve, once you define the contraction ratio by the inlet and the outlet, right? So and then you can decide what is the length. You can decide what is the length and just insert on your formula. The formula says the normalized x is x prime by L, by the length. So when you have the dimension of inlet and outlet, and you decided the length is the same as twice the inlet diameter, then you have everything there.
Because if we put shorter length, then we'll will not allow that flow to contract to the dam.
Okay, it's again a kind of experience. Most of the times, that's what you see. That is, it is recommended to have one, the largest diameter. And the result I've seen at Meta's paper were done for such kind of length ratio to diameter to an inlet, 1 to 1. So I rely on that. Of course, as we said, as long as it is, it'll have more time to adjust itself, but then it'll accumulate boundary layer thickness, which you don't like. So this is a trade-off. You want short one, not to have boundary layers to develop, but you need also aspect ratio or area ratio big enough in order to get a good acceleration and attenuation of noise. So something between 6, 7, until between 6 and 9, we do the job. The papers I've seen, they were between 7 and 9. Here in Jerusalem, I made it 9. In Tel Aviv, I made it almost. You can calculate how much is it, about 8, I think. So it's quite good.
We should have sufficient length, otherwise flow separation may take place.
Okay, that's what I'm saying. One dimension is okay.
Yeah.
One inlet diameter, that's sufficient. That's acceptable.
Nowadays people they are talking about larger contraction ratio, like 10, 12. So what is the reason behind it?
The only advantage, you ask about the reason why people are looking about larger area ratio. The only advantage there is that you attenuate and you are decreasing the disturbances that you got in you did manage to get rid of in the settling chamber. Okay, if you have any turbulence level that you remained within the settling chamber, this aspect ratio, this area ratio will attenuate the level of turbulence with respect to the area ratio. So as bigger the area ratio, turbulence level will reduce. But again, I'm saying you will pay once it is. If it's too short, as you said, there is a risk of separation, because the one important parameter of separation is the pressure gradient, and once the pressure gradient is too high, you'll get separation there.
But sir, this is contraction.
This is contraction. How separation will take place?
When there is a change in the curvature, the flow is not able to maintain the curvature. When you have a very high area ratio, you must have a very high curvature after the inflection point. So close to the wall, flow may not be able to follow the curvature.
This is made of wood only, sir, but the life of this wood.
I count on it.
Huh?
I want to be there when it is dying. It's okay.
It may be a special wood.
There is some treatment for this. They have a treatment against insects, and it is covered and polished with kind of lac, and it's very treated. It's treated very well. No issue. Okay, so now I would like to move on to the honeycombs.
So in one of the texts they were talking about some tapes at the exit of the contraction just before the
About what?
some tapes they put on the wall.
For what?
So it's got something to do with the boundary.
I don't know. I make it, but it's wrong. I mean, it's because the connection is not perfect. Once it is not perfect, you would like to smoothen it in some way. But otherwise, I prefer that the connection will be smooth. That's enough. Yeah. Because geometrically, you said the first and second derivative they are zero. So it has to be matching there. Only if one of the contractors was doing not well, then we get some problems. Yeah, this is one of the important. I mean, the nozzle is most important issue because once you design and you manufacture the nozzle, you will not get back to it. It's the heart of the issue here. So once you design and you manufacture the nozzle, it's there. So you better take care of it on the first place. And second, you make sure that the connection with the test section is smooth.
So how did they bring that conviction in the wood?
They treat it. No problem for them. No problem for Indian carpenters as well. They do nice jobs, I see. I'm sure. You take 8 millimeters wood and maybe even you wet it something. They have their way to treat it. So honeycombs are used to straighten the flow. They are not so much in the game of attenuating the turbulence level because there is no any mechanism here that will suppress vortices. It will only direct your stream. If there is any mechanism that brings you the flow not in the main direction, then it will straighten it. And I had a good demonstration of it recently in our little tunnel. On the contraction, first of all, on the ellipse, the entrance. At the last moment, I was adding these elliptical sections, so like a bell mouth, it will be smooth. But still, even then, when air is coming in, there is a little bit of separation in the entrance. So, first thing, we put there a honeycomb, so make sure that any flow which is not in the main direction will straighten. And I saw it, we saw it. As I told you, I recommend, and we do it, for every element like this, we put it in a drawer so we can check how it reacts without a mesh, with a mesh, without honeycomb, with honeycomb. We had all of this. So by mistake, they were running without the honeycomb, and even in a manometer, simple one, just inclined U tube, 30 degrees, they saw how the water fluctuated when the honeycomb was not there on the sensor that was next to the wall. Once they put the honeycomb, it's straight. So it straightened the flow. Now, in another occasion, this is in the open loop. In the closed circuit, you would put the honeycomb just behind the last corner, the fourth corner, to take care of big eddies. Namely, when you have a big eddy, it means you have different velocity vectors from the main one. So once you have this honeycomb, and honeycomb is these are cells at the size of several. I mean, in the small wind tunnels, there will be several millimeters. In the big one, it will be bigger a bit. But still, there is the ratio between the diameter of the cells and the length, which should be something like 9. At least 6 to 9 again, preferably 9. Means the honeycomb will let only eddies or vortices of the size of the cells. So it will kill any bigger disturbance than that. So it will decrease the size of eddies, and consequently it will reduce the disturbances to lower level. So it is not a mechanism to attenuate turbulence, but just because it is straightening the flow and decreasing the size of disturbances, it will decrease turbulence level anyway. But this is not a mechanism or a method to gain and to reduce turbulence as later on. Later on, you need the meshes, the screens. So you see here the terminology, parameters that are related to the honeycomb. By the way, honeycomb can be made of also circular tubes. If you're going to build your small wind tunnel, you just buy hundreds of straws and connect them, and you have a nice honeycomb. So, as I said, length to diameter will be 6 to 8. I said 9, 6 to 8. So you need at least 6 to 8 diameters length in order to get some results and effectiveness. Second parameter you look for is the porosity, where porosity is the area that can flow divided by the total, namely the total area minus the substance, the area of the substance. And this also you expect to be greater than 0.8.
How to decide this diameter of honeycomb? Diameter, that dimension.
Yeah.
Because like settling chamber, whatever the size, based on that we need to decide how many slots you want to put.
You want it the little as you can. The little as you can. Only thing you should pay attention and see how much you're going to lose, what add loss you got for that. But you would prefer to have it smallest. You want the smallest eddies, vortices to get through. It's a filter. Okay. So it's a trade-off again with what you find in the market as well. You will not build this with straws if it's a huge wind tunnel. If it's a small one, no problem. But if it's a huge tunnel, you will buy something commercially. So first of all, you will look what you have in the market. So you take the smallest if you can. But again, you check what your loss going to happen. Yes. So this is like that. It is not so critical, since the really activity towards attenuating the turbulence level are the meshes and the screens. They are more effective. So this thing is not so dramatic. You just prefer to have it there to make sure that big structures, fluid structures, will not sweep down to your test section.
There's a transverse motion also instead of streamwise.
Yeah.
That can stall the screen. So then the performance is bad with the screen. So we want very straight flow before the screen.
Yeah.
That's what they say.
No, I mean, screens will not kill eddies. It will only attenuate.
Yeah.
Screens are not able to take care of big disturbances. Only they press them, whatever they try, they can make, but vorticity will remain, will be preserved behind the meshes. You'll find it. So you have to make care to make sure that you get into the meshes to the screen with lower disturbances, and this is by that. Well, the loss across honeycombs is given elsewhere. This time I was using Eckert. There is a Eckert of NASA technical note D8243 from 1976. They even wrote a Fortran program for all these calculations. I don't think it's necessary and worthwhile to go through those, even if you are doing it. Though they were doing a very good work, it's enough that you use their calculations and formulas, and you work it yourself. So the loss coefficient there for the honeycombs is given in formula 414, 1, and then you need another factor, which is lambda, and the lambda is given in another formulas. One is for Reynolds, depending on the roughness height of the honeycomb material, and there are two regions. One is below 275, one is beyond 275. So because the main loss is because of friction, of flow within these tubes. You have endless number of tubes. So the factor here is the Reynolds number for those tubes. So you have this calculation. And this is not a big loser. I mean, honeycomb is not, you will see later on the distribution of loss across the circuit, and you see honeycombs are not contributing too much for the air loss. The next element we are going through are the screens. Screens first we look at the loss and definitions. You have the wire diameter and the width, which is measured between one side of the wire to the same side of the next wire. So with that you can calculate again the solidity and the porosity, which is they are complementing each other to number 1 to 1. Because I mean this is the percentage of porosity and solidity of the mesh. So porosity is 1 minus the diameter of the wire divided by the distance between wires, power of 2, and 1 minus that is giving you the solidity. And Reynolds number of the wire is simply the velocity across the mesh times the diameter of the wire. Now, we are using the screens to reduce turbulence level. As many as screens you have, you will reduce turbulence level. The correlation or the connection between attenuation of turbulence level to the coefficient of loss is 1 over 1 square root 1 plus k, when k is the coefficient of loss. And typical numbers are of 20% or so, if the mesh is dense enough. Typical porosity of screens we are using is between 0.5 to 0.8. So what we usually do is having series of screens, starting from the rough ones and ending with the delicate ones. And in Tel Aviv, I put 3. Also in Jerusalem, I put 3. I have not yet made turbulence measurements there, but it looks smooth anyway. We'll see shortly what happens there.
to be distance between these screens? 1, 2, 3, 4, 5, suppose we are using. What need to be?
Hundreds. 200s of mesh dimension, of hole dimension, something like that. Hundreds of them. There is some figure I can't recollect at the moment, but it's something like several hundreds.
That's more than 100.
Yeah. Actually, what you want is that the turbulence that is created by the wires from the first mesh to decay somehow. You don't want to work to have extra work on because you have a screen there. So you wait till the turbulence that is created by the first mesh decays. So this is decays, and so forth.
So this screen and honeycomb,
Yes.
both, honeycomb is for straightening, and
Yes.
this is for reducing the turbulence intensity.
Yes.
But here, if you see, structure is square in the screen. There it is.
Okay.
7. So whether this
It's not a structure. These are only wires. It's not a structure. Wires. Circular wires. You can look at it as cylinders. Cylinder is creating a vortex shedding from Karman shedding. You remember?
basically, I just want to know is honeycomb, like more honeycomb structures also. If we keep, that won't do the.
Won't help you nothing. It won't help you. It's a waste. Because once you straighten the flow, no argument to put another one. It won't reduce anything. After you straighten the flow, you want to attenuate turbulence level.
What is the mechanisms of the screen by which it is reducing the turbulence?
It's again, you force flow structures to get into some contractions. It's miniature contraction. Look at it like this way. Once you have contraction, everything will decrease. So you can look at it this way. Yes.
So would it be helpful if we kept 2 or 3 screens in a decreasing order of dimension?
That's what we are doing. That's what he said. We are placing series of screens on a decreasing size, porosity, and as many as you put, you get a reduction in turbulence. No, it's just additive. No issue, no question. You want less turbulence, you put another one. But you pay for it for the head loss. So if you don't care or you don't mind about the velocity too much, and you care for the intensity, you just put another one. So another recommendation outcoming of your question is, you may, if you don't know really what your need will be for intensity, keep another drawer empty. Or put as many as you want at the beginning and just take out when you don't need very low turbulence intensity. Not to lose energy, right? I think we're a bit innovative in this. I haven't seen too many wind tunnels that have this option to control this number of meshes and screens. So,
Will it help, sir, if we put variation of sizes, say, since in the middle of the flow, turbulence is more, then there we keep smaller, and if that we do, will it help?
I want to understand what you're asking, please.
So my suggestion is here in the core region and out of
No,
the
you claim something that I'm not sure I can accept, except very close to the wall. Very close to the wall. Everything will be similar. There is no reason out of the boundary layer turbulence level to be different.
no reason.
No reason. Of course, as closer you come to the wall, it will reduce. But this is not the issue. You care about the free stream
No, what
level.
I am saying is that by this, if we can minimize some loss,
By what?
by actually we keep the grid
Yes.
very dense type.
Yes.
It's small.
Yes.
Then loss will be more.
Yes.
If it is more, then
Yes.
loss will be less.
Yeah.
So that way, if we can.
But then reduction of turbulence is in that ratio. You see it in the formula for 516.1 as you want to reduce your turbulence more, K should be less. I mean, and K will be less, you see later on, according to the solidity. I mean, solidity. As much as solidity is less, namely less dense, also the turbulence level will be attenuated less. That's not what you want.
Okay, anyway, I understood that.
And intuitively, once you open up the mesh, the effectiveness will reduce.
Right.
So,
Now my point is, if turbulence is small there,
yes.
then by
Okay.
opening up will not
Yeah,
harm.
naturally. That's a trade-off. That's why I recommended you to put in, to use draws for your meshes, your screens. If you want only one screen, prepare screens of different sizes and check what you want. Trade-off. You want this turbulence level, you put this screen. You want this, you take this out and this. I have one. I put, as I told you, I put honeycombs and screen downstream, ahead of the fan, not to prevent from upflow disturbances. And we found immediately, obviously, that the screen close to the fan is much more effective in terms of loss. Why? The velocity there is the highest. So nothing easier than just take out the draw and forget it. If I have to pay in power 5 meters per second in my wind tunnel, and it remains to check how much it is really affecting. I was not following. Again, this is something I think I was not seeing too much. I think in this also will be we'll have some new information. So
What order of loss you see in honeycomb and screen compared to the overall loss?
you'll see later. Later you'll see. It's there. So we have a calculation, a formula to calculate the loss in a mesh. It has two factors. One is K mesh, which is taken as 1.3, just like that, and the K mesh is 1.3, and the KRN is formulated empirically as a factor of Reynolds number for the wires. And you see that for higher Mach number, Reynolds numbers, this factor is 1 only, and the other one is close to it. The last day, we'll take some example of a wind tunnel that they were doing this exercise. It's a nice exercise. They built a 50 centimeters, and they show you step by step how to choose their elements and how to calculate the loss. So for this wind tunnel, it's let me see. I'll mention them. It's a book by the name of Nova Science Publishers, Models and Experiments. It's written there. The names of the writers, authors is Burska, Lanzafama and Massina, I think, seems to be Italians. It's a nice work. Nice work. I didn't like their nozzle that is made of metal. You see the welding there is soldering there. The welding there is not nice. The work, it's not smooth. And you don't have any way to recover. Once it came out for the construction, that's what you got. Where it happened to us in Tel Aviv, I didn't tell you the story, that the kitchen carpenter was making he made two nozzles. The first one, what happened, my good student forgot that he has to define what's the material cut that he has to give. It's not the same size as the contraction because it is bent. It bends. So you have to give the carpenter the relation between the bent part and the straight one. Okay. So this thing he caught him on time. He didn't cut yet. So he gave him the formula because he had a numerical machine. So he cut the material according to simple ratio between bend and not bended. There is a formula we found out, but it's built in today in the solid programs. Once you design something, it will compute for you. But we just, as an exercise, I gave it to him. Okay, so we gave him this formula. The guy cut. As usual, students have exams. They don't have time to follow up. So he came a week later. He said, come with me, see the nozzle. I want to show you there is a nozzle. So we went to see the nozzle. And the first thing I took a meter to see the length of the nozzle. And it came out 10% longer than it should have been. How come? How come? So we asked the guy, what did you do? So he was just connecting the edges. That's it. And why? By connecting the edges, he thought it'll be, the formula will follow. The rest is history. So no. At that point, I had some time to convince my student that it's not unique. You have to define the points along the curvature that it will follow them. He couldn't accept that, so I took him to a plumber shop there, and I showed him this pump that you can have. The pump looks like a contraction, right? The one that you use to release your pipe. So you can, by pushing and pulling, you get different nozzles. So that convinced him. I told him, take this and go to the conference that you're going to present your paper and show them why this can happen. So the second one, it was perfect. Second one was with the frames and the curvature and everything went well. So you have to really follow up your contractor and your carpenter, whatever you give, because they're not building wilderness every day. They have good hands. They know what they're doing. I count on them, but we have to follow them. So this nice job that they were doing, they were going step by step on every section, and they computed the loss. And you see here the contribution of every element. This is in page 19. Page 19. You see the table, and then you see the histogram for every section. So it jumps very clearly is that the first diffuser is the worst part. And then the smaller corner. Smaller corner is the second contributor, and the other smaller corner. Why? Why?
Just after the pan.
No. The first diffuser is after the test section. Why is it like that? Anybody can tell me? Why they are the worst?
Because after that there are more diffusers and that will more on the top.
Almost the correct answer, almost. because there the velocity there is the highest. Where the velocity is higher, then the loss is higher. So diffuser is the first one after the test section, and because of its contribution by the expansion, it has, and also it is longer than the test section, it has a higher loss. Anyway, it's almost linear. You see the loss of the test section, the first one is almost 1/3 from the diffuser, even less, a bit more. When the diffuser is 3 times the test section, and you calculate your head loss there, it'll be like that. And then you see that honeycomb is not a serious issue, and screens are issue. You see the screens are the second contributors after the corner there. Though they are located in the settling chamber and they are not facing a high velocity, they are contributing to the loss. So you see the summary or the accumulation of total pressure loss, and with that you get into your supplier of fan. And everyone has its own way to plot. One thing is the pressure from the tunnel is the same way. It is exponentially or grows. This is the two lines, the solid one and the broken one. Solid one is the closed test section, and the broken one is the open test section. And this is growing exponentially over the power of 3 to speed. That's the pressure is going by second, by power of 2. So, and you want to find the point of the working point of this exercise. It is not on that graph. Somehow, I think the calculations he made was for 30 meters per second, and I can prove it from his graph, from his plot. The next plot, if you take, you find out where you have 140 of static pressure, and you cut it to the test section, you find out that it is 30 meters per second, or if you calculate the flow rate, 30 meters per second times a quarter square meter, it's 7.5 meters per second speed. I'm sorry. 7.5 cubic meter per second will give you, you will get out of 30 meters per second speed. You just multiply 7.5 times 1/4 square meter per second, you get the flow rate. So if your speed is 30 divided by 4, it's 7.5. So you get 7.5. 30 is the speed, I said. You multiply by 1/4, you get this flow rate. So the point that he was calculating the table should be somewhere here. 140, you go here, and you cut it somewhere here, and it's 7.5. So the working point that he was demonstrating is 7.5 cubic meter per second. Though you see their choice of fan was higher. They pushed it higher. They didn't want to be on the limit, so they pushed it to the next velocities, even they were theoretical. They didn't reach them. The maximum speed was 32, 34, but they chose the fan that could give them that that flow rate. We'll work it out on the last day. Hopefully, if you have an access, we need an access to the internet, and we'll load down one of the suppliers' programs how to choose the fan. Okay, with this we finished for this moment, for the day, the design, the loss, the calculation of loss, and we have in mind more or less what we are up to when we have to build up our own tunnel. Last day will give you final confidence that you can build it yourself. I don't guarantee you that out from here you go down to the constructor and build your own wind tunnel, but I'm sure with some work you will be able to work it out and make it. So we'll move on to forces and moments measurements. Unless you have some questions regarding what we discussed, we'll move on. Yes.
Since we are selecting an axial fan,
Yes.
will we have any spiral in flow? The flow spiral?
Yeah, that's why I put. That's why if you are sucking, first of all, once you are sucking, on blowing you will not do that. On blowing it will infect your flow downstream for sure. Once you suck, the effect is less because it flows out. But there'll be upward influence. That's why I put both honeycomb and screen there in order to straighten the backflow influence. It still remains to check what is the real advantage of it, but sure it's there. Just this afternoon I wanted to check if the venta is flowing out of the window or sucking it in, flowing out or sucking in the bathroom, and I put my hand, and I really couldn't figure out if it's blowing out or sucking in because it was noisy, very noisy. So this is an answer. I think it happens. It's right. It is right. You have to take care of that. Okay. I didn't work too much to give you a better figure of this axis, because we are not going to work too much with this, just to give you some idea that while dealing with balance in the wind tunnel, we have to deal with different frame of references. You have the balance frame of reference, you have the wind frame of references, you have the body frame of reference. At least 3 you have there. And you have to take care and know exactly what you're doing to transform from one system to another system. So this is the essence of this confusing thing. I took it from a book where he was trying to show the Euler transpose of angles when you change angles, how it goes from one system to another, but we're not going to do that. So the procedure is simple. We measure forces and moments, reduce it to coefficients, non-dimensional. We will discuss this. And finally, when you try to implement your coefficients, they should be expressed in body axis, because you are going to use them in the vehicle. You're going to use your coefficients to see how efficient is your vehicle first, and then you may need to feed it to your control loops. So they have to be expressed in body model axis. Just terminology of those axes and moments and names. There's a nice figure of this aircraft and 3 axes. But what is misleading here that the axes are not following the right-hand rule. So it's okay, you have to be really careful here. The aircraft is flying forward. It's flying forward, and no doubt, normal force will be vertical to the body axis. Normal force, no problem, it will be upward. Pitching moment, if you're flying forward, whatever will pitch you nose up, nose up. So the rolling arrow showing well, but the direction, right-hand direction shows bad, you see, because if you are rolling up, your axis should show right way, and this one showing left way. So be careful. What important is that you keep your axis wide. You're flying X, right and Y to the right, and Z facing down. And according to this, you define your moments. Pitching moment is pitch up, and Y is to the right, and yaw moment facing Z and clockwise. Here it's okay, it's showing clockwise. It's a bit difficult to see the wall, but it's again clockwise. And clockwise will be forward direction. So the rolling, the moments are showed well, but the axes are not. But what important is you remember this terminology and the principle of choosing your axis, body axis. Now, tell me.
These movements are following right-hand rule, sir?
Yes,
But
should.
not forces.
Everything's for. Okay, no, you define normal force. Yeah, normal force you define up, positive, because it's close to lift. Lift is always showing facing up. Only moments, yeah, you're right. Moments are following, but the normal forces, usually normal force is like lift upward, and axial force, again, will naturally it's going same as drag, backward. Yeah. And side, only side, we look. Anyway, when you are working and you are testing, you have to make sure your sign convention is acceptable by your user, no matter what you are doing. But we start with something that reasonable, and then just make sure that your user, your customer knows what is your sign convention. Your sign convention, your axis will not change the forces. The forces are there. It will not be affecting them. Only the transformation will be affected, and you have to make sure they know what you're doing. So we can mount models in the wind tunnel several ways, either by struts, and they can be one strut up to 3 struts in the low speed, and they will be connected to external balance, which is outside the test section. And when mounted in internal balance, they'll usually be only one strut. Only one strut in different configuration, different setup. It could be coming from the floor, could be coming from an arch, Could be anywhere. The point to remember is that in low speed or in high speed you will not see struts. You will only see one sting, usually coming out from the fuselage. But sometimes if you have a twin engine, you need to have a fork, 2 stings, or maybe one dummy and one real one, because you will not put 2 stings to measure forces. You use only one. I think it's about time to have a bit break, and we'll go deeper in that.
the guest house itself, in the banquet hall, which is just above the guest house dining hall. Yes, technology guest house. That is the main guest house. At 8, 7:30 to 8, that is the time issue.
Oh, this works. It works, no?
I have some other announcement also to make, but that I will do later.
It works.
After this class.
You want to change?
No, the technology guest house was mentioned.
Why, you need it for the other system? Why will you change? It's good. It doesn't work. Okay, good. Okay, we start. Now, we are experts on what's going on the ground in the wind tunnel. Everything is known, and we go ahead and see what's going underground, below the test section. Below the test section, you'll find a very complicated structure. Very interesting structure. You find it in many wind tunnels. The external balance. You have frames on frames on frames per each axis of motion. The basic is rotation. You see the gear on the basement that gives angle of yaw, and the struts usually will give you the option of angle of attack. And the rest, through the struts that are connected to the frames, it depends on the principle of the balance, how it works. There should be 6 measuring elements for 6 axes, 3 moments, 3 forces. The type of measurement elements depends on what you're doing there. So formally, as I told you, in the old systems, older systems, they were using the principle of beam balance. So on every axis, you will have a balancing component that will be balanced by a move of weight, and you move the weight by stepping motors, and the way once the frame is balanced, let's say frame is sitting on frame and they are free to move. So, but only to the extent that the weight is the counter force that applying to every axis. So once the force is exerted, there is a closed loop that will make sure that the weight will move until the beam will be sitting to balance the frame. So this is an old procedure. I don't believe anybody today who is starting to build such machine will work on that principle. Today I believe everybody will go for the strain gauges, because then there is no movement, no need to worry, and most important thing is accuracy and frequency response, because you can imagine this way of balancing is very slow. You can measure only average forces and moments. The moment you want to measure dynamic, you have to move to strain gauges. So here you see the old principle of beam balance and external balance with load cells. I'm not sure you can see them, but you can see in every end of a rod, a pillar, there is a load cell with strain gauges. So for every axis, you must have a measuring element. Schematically, you see it on the next slide. If the frames are representing the structure of the balance, at the end of every frame, of every rod, you see a measuring element. You see altogether 6 elements, 2 for every even 3, doesn't matter. You must have 6 because you need to have the capability to express 6 forces and moments. And now if you look at the equations, you see the connection between the forces and the measuring elements. For instance, the first one, axial force. Axial force, which elements are measuring axial force? Tell me. XD and XL. So you simply add them. Side force, you have only one element. Y, double Y. Normal force seems to have 3 elements. Now see what happens with the moments for the rolling moment. Which elements are taking care of the rolling moment? Why? First of all, where are you taking your moments calculation? To which point? That place is called BMC, balance moment center. You have to define where is your balance moment center, because when you have to transfer your forces and moment from the balance coordinates to body coordinates, you have to know exactly where is your balance moment center. So now we are calculating the forces. First you calculate according to the balance. You measure balance measuring center, moment center. So rolling moment, you have to multiply the force measured by YY to the arm C2, which is from the axis of YY to the balance BMC, and so forth. So this is the way you can build your own external balance. Just make frame of references, put load cells, and you measure. Very simple. And you need only one axis, measuring only one axis in your load cells. They are very costly. I bought to measure normal force and axial force in the wind tunnel, and I think it cost something like it will cost $5,000. $5,000. How much is it? 5,000. 3 crores? 3 lakh? 3 lakh. 3 lakh. Yeah. Only one component. I mean, these are 2 components of one system. So it's very, very expensive, those things.
The central part is that is a stiff.
This is schematic. This no. This is below the floor of the wind tunnel. It's schematic. It is schematic of the external balance. It's not a real structure. It's not a real structure.
This is the model is to be connected, no, sir, for that.
Model can be connected anywhere. Model probably will be connected higher than that, beyond that. This is below the floor of the wind tunnel. This is below the floor.
And the model
See the previous photo. See this one. You see? The balance moment center, the BMC of the balance, probably, yeah, it could be in the aircraft also. Imagine it's a virtual point. It could be in the
So
aircraft.
it is supported at 3 points.
Three struts.
Model is
Yeah.
supported.
Yeah, that one is only schematic. You can support it with any numbers from 1 to 3, and no need another one.
So where it is supported, that it won't disturb that flow, no sir. The wing, it is given as supported the wing. So locally, there the flow may get disturbed. I think.
Okay, now we are talking about balance, not about flow.
So what is the means of transferring the loads on the external balance onto the model?
Through that
Struts. The
rod,
struts.
yeah.
The struts are transferring the loads. The struts, the three pillars coming down from the model, they are transferring the loads in all directions.
So in some cases, wires also used, no, sir. Wire, flexible wire, or supporting the model.
Not too much. I don't see too much. No. It could be. It's cheap. It's cheap installation. Yeah, you could attach your model to wires and string it and all these things. I don't know.
You don't have so much interference with the struts or so it gets low.
Struts are not a big deal. Struts you can. I mean, since it is low speed, you can get rid of the disturbances and you can eliminate the results and get better. Though the flow is disturbed, you can get corrections. You get corrections for this
I
situation.
think it mostly depends upon the kind of measurement we are doing. Because at height, if speed is higher, then the string kind of.
If
The speed is higher or you have high resistance from the model, then the strength will be tricky to manage. String balancing.
yeah,
Wire
yes,
will be tricky to manage because they tend to maybe move a bit.
yeah, they won't be stable. Yeah, it could be they won't be stable too. Yes.
So here in the beam balance, where the model is connected, sir?
Instead of load cells, imagine every rod that at the end you see load cell. You see here load cell. Wait, it's very difficult to control this stuff. These are load cells. Here, you see, all these are load cells. Imagine that the rod is connected to one end of the beam.
Here also same.
Yeah, yeah. You have 3 on the floor, and you have 2 on top. There are 6. Don't worry, they are there.
They can't do dynamic measurements. Like
When it is a beam, when it's the beam,
yeah.
because it takes time to balance. A beam balance. Are you having this in your clinic, in your hospital? When you go, sometimes you want to measure. You have to measure your weight. So there is a mechanical one that you stand on it, and you have to balance it with the weight. You remember? Okay. So this is the same principle here. There is a stepping motor which moves this weight until it equals the load. So it takes time. What is the frequency response of this kind of control loop? It's 1/10 of, I mean,
Now
it's
still the beam balances are in use, sir.
sure.
But we can use this way with the load cells.
Yes, you're right. You're right. That's a good upgrade program for those who are still running. I hear these stories in my place for a long time. But instead of changing the load cells, these 2 load cells, what they do is they manufacture a new setup to get sting balance on this table, turning table. So they don't use the balance, or they use it as a redundancy. So they connect a sting balance capability to the rotating table, to the balance. They use the struts to hold sting balance. So the aircraft is sitting ahead, no disturbances, and you measure with sting balance, high frequency, no problem, and if you want even, you get a redundancy result. So instead of replacing the whole system down and try calibrating the big headache, they just replace the thing with sting balance. The problem is, if you come with a big aircraft, this is good if you take aircraft from the supersonic or transonic tunnel, which is 1 to 15 scale, and you go to the low speed, they take the same model, so no problem. But if you we have to measure forces for business jets, which is 1 to 5, 1 to 6 scale, 70% from test section. It's a big one, it's a huge one. You cannot hold it with sting balance. Still, you get only static measurements. Anyway.
So for business jets, we cannot use the sting balance because the capacity may not be.
Because what?
For business jet, the model is so big, the loads are also high, and the internal balance cannot be capable of.
On the low speed, because of the size of the model, it's impossible. But yeah.
So we have to have this type of measurement only.
Yeah. Yeah. And usually, anyway, the measurements in the low speed are limited in purpose. I mean, they are limited to takeoff, landing, to low speeds. You are not expecting to get meaningful results for transonic speed in the low speed. You're testing in low speed, you get result for low speed. So when are you flying low speed in business? Just takeoff, landing. That's it.
So do you have a similar configuration and you have turntable and you're putting like a automobile model and you're
Yeah, sure. I mean,
abstract.
you find it in automobile testing this way.
External balance should be
Yes.
below the
Yes, yes. This is exactly what is used for. Yeah, for testing automotive models, you can use this easily.
What is the use of a stepper motor there, sir?
Tell me.
External balance system. A stepper motor, use of a stepper motor.
Yes.
What is use of a stepper motor there?
It's only for the movement, for the rotation and the pitching in the pitch angle, just for 2 angles.
During test, nothing it has to do.
Why not? If it's a continuous wind tunnel, you can change anything. You can change yaw angle, pitch angle. You have time, all day.
You told that you will use it. Nowadays they use internal balance also, and what if the external setup is there, they use external also.
Yeah.
So that because we have two balances,
Yes.
won't there be a load sharing between this balance and that balance?
I'm just saying it's a possibility to use both systems, but usually they don't use both systems. Nobody is looking for extra work. If they measure in the internal ones, it's sufficient. Yeah, it's a waste.
so you have one of these, right? External balance or external balance.
I'm saying that for the external balance capability, instead of replacing the beam balance to strain gauge, what people do is fitting some kit in order to be able to connect the model to a sting balance. That's what I'm saying. So you use the struts only to hold the system, this kit, and you use the struts only. Depends on what system you have. Probably use it both, just to move the model, just for moving. Pitch up, pitch and yaw. Pitch and yaw. This kind of arrangement was for a long time back. It's not an issue.
The string gauges will be inside this string which is holding the model.
Strain gauge will be, we'll talk about it, we'll show it later. Yeah, we'll show it. Strain gauge will be within the model. external balance calibration, I must admit, rarely you see the people calibrating this kind of balance. It's very tiring mission because you have to build specific frame in order to calibrate your balance. You have to load every axis according to a plan. Now, the minimum calibration metrics that you are using is 6 by 6. Imagine that you have 6 components. You call them FJ, and you can read the voltage from component J. J goes from 1 to 6. And then you exert forces on all the components. If I call it here, again, I call it FI load. I call it, on every component I have a load. So I have 6 components that I'm loading them, and I read 6 components readouts. So we have 6 by 6 components. We have every readout is actually a combination of the loads that I'm exerting on all other 6, assuming there are cross influence between the channels. So this is the minimum I would like to do, to have 6 by 6 matrix in calibration. And it's not so easy to load the balance on 6 axes. You need a special arrangement for that. At least if it's a dead weight, imagine for every axis you have to connect it with some wire around some roll, and then you start load. And if you do it manually, you can give up your condition, your Pilates lessons. Then you don't need anything else. You can make your conditioning there. So for 2 weeks you can go there. That's what they were doing. You just need a plan to load all the combinations of loads from all the axes. That's the manual calibration of the external balance.
All the components we are loading simultaneously or
Yes.
one by one?
Simultaneously. You want to see the cross interaction between the. That's why 6 by 6. Otherwise, you would load it one by one, and you'll have only 6 components, which is not so accurate. Okay. So we said it will be applied mainly in low-speed wind tunnel because you don't expect in blowdown to work with this such of balance. It will react very slow, and also you have if you have the struts, always you can go with one sting. That's not an issue, but you will never waste the time. For sure, not for beam balance, and there is no need to go for strain gauges outside somewhere else you don't know. Once you have a good installation for sting balance, which we'll talk later. In order to get rid of disturbances from the struts, there is a full procedure of how to eliminate the disturbances. I mean, we cannot get rid of the influence. Once the flow is affected by the struts, it's there. But you can measure and find out what is the influence and try to correct. So what we do, we do 2 things. One is, and I didn't explore it in the material, but it's good that you know, generally speaking. I hope you'll follow what I'm saying. One thing is use dummy struts. that are installed. There is a dummy table, turntable, symmetrical to the real one, and you have dummy struts, which are not sensing and touching the aircraft. And then you make a sweep and measure what is the difference between with dummy struts and without dummy struts. So that gives you what is the effect of struts on the other side, though it is not symmetrical because one side is upper side and one is the lower side. In order to complete this correction, you invert your model and do the same as inverted one, and measure it inverted, and again with dummy, and then this way you can reduce your disturbance by calculations. But still, it's not optimal because the flow is disturbed. But to an extent, you can get rid of it. No big issue. So, since we know there is a disturbance there, we are not able to run it in transonic. In transonic, we are using sting balance. In this photo, you see Hornet F-18 in NASA's one of NASA's wind tunnels. You see it is connected by one sting coming out from the tail, from the exhaust area, and it is connected to kind of, it seems like an arc. You see in the back, in the dark, there is it's like a long pillar. It has a shape of arc, and while moving along the arc, you get different angles of attack. This is one way of doing it. There are other ways of getting this sweep, like with some parallelogram, when the sting is connected to 2 points, and then you have shift of 2 rods, and it lifts and makes this angle of attack on a model card which sits behind the model. So the sting balance is within the model, and it is actually made of steel usually, but made of steel but weakened along certain sections. And on those sections that the structure is weakened, and you know the stiffness of those sections, you glue strain-gauges, which are deformed according to deflections of those of those flexures. Let's say you take a ruler, take a metal ruler, and you glue on it strain gauges, 2 strain gauges, and you connect it one end, and the other end you load it. What happens there is it's elongated. It elongates also the strain gauges. Strain gauge is an element in the bridge, in Wheatstone Bridge, and once you change the resistance of this strain gauge, you can measure how much it was changed, how much it was elongated, and according to that, what was the load. And the more strain gauges you have for an axis, you get more accuracy, because you have more input to your calibration.
Professor,
Previous slide.
is it necessary to put this nose in a particular location and while doing U motion? or measurement, that point need to be steady, or like suppose this is nose.
Yes.
Okay. For your study, it need to have this position to be fixed, and you like this, or maybe it can move both the way. This point need to be steady.
I understand. I understand your question. You're asking. Let me see if I understand your question. You ask if it's important to keep, let's say, the nose of the model in a spot whenever you are yawing the model.
Yes.
Usually, what you are keeping fixed is the center of gravity of the model, as it in life. What the maneuvering of any model, any aircraft, is around its center of gravity. So it's a virtual point in the model because you don't care about the center of gravity of the model. It has nothing to do with the prototype, but you should know what is the center of gravity of the prototype, and you would prefer the model to rotate according to the real aircraft center of gravity. So this means the nose will move. It won't be staying on the same spot. But you expect the conditions to remain. Wherever the nose is, you expect the conditions of the flow to remain the same, so it won't change your results. Is that answering? Okay.
Is there any criteria that the weight of the model should be this much like that?
Now, this is a question of beginner, but it's good. Everybody else will get it. Is the question if there is an importance for the weight of the model? Is this the question? So, once you are measuring the aerodynamic, nothing to do with the mass of the model itself. In these forces and moments, what you are worried about and you are taking care of is only the shape. And you make sure the shape of the model will not deform. If you make it of weak material, out of loads, maybe your wings will deflect, your fuselage will deflect, which some things that happens in life. But unless you are simulating exactly what happens in life, it's wrong. You would like it to be stiff and check it as it is. And if you need to check what is the stiffness, like in flutter, then you build up a scaled model for the stiffness.
This even applies to the store separation also.
We'll talk about it later. Store separation is a different.
And when I'm using internal balance, should the balance that N and N2 should it lie within the XCP of the model? Center of pressure location.
You would like the balance to sit. The question is where to put the balance relative to the model. So you would prefer the balance to be the center of the balance, the BMC, be closest as possible to the center of pressure or center of aerodynamic center of the aircraft. So you will not overload your balance. You want to get better resolution. If you start loading your balance far away, and you get right from the beginning parasitic moment, then you lose a lot of resolution.
No, if the center of pressure comes to near the one of the cell, then the accuracy will deteriorate.
You don't use only one cell. That's the point. You don't use only one. You use several one for each component, so it won't make a big difference.
Usually we say that for normal force they use two strain.
That's the minimum.
Yeah.
Because
so when they use two cells, let me my center of pressure location is at 1+1.
yes.
So it will deteriorate instead of if I have in the middle.
Yeah. It will be disturbing. That's why, preferably, as in this example that I'm showing later on, they have at least 4 strain gauges for each component. So it will be less sensitive. Now, internal balance calibration, usually recommendations are for more matrices, more complicated. In the example I was looking for, they were dealing with only 5 components instead of 6. and they were calibrating dead weight, the dead weight method. Dead weight, everybody used to do it formerly. Namely, you install your balance to a sting in the lab and load it simply with weights. Again, a good conditioning work. That's what happened when I joined the industry. I was shocked. I see people that working there. I was going to play basketball. They were loading these things like this. I said, and then after that they were going to the conditioning room and lifted weights. Why? They could do the same there. I told them, instead of lifting the weights there, you just keep going there. What are you doing? I mean, why do you go and lift weights in the conditioning room? Fitness. So in this example, they are taking 210 points weightlifting, but they are able only to have 3 components simultaneously. It's a problem when on dead weight, hand dead weight, and I'll let you something. And on dead weight, maximum you can have combination of 3 loads. It's force, moment on the same axis, and also on an additional moment, the rolling moment. Now I have a suggestion to my friends when they start building their calibration machine.
Loading, we can have pitching moment also.
Yes, you just roll it from pitching to side, going moment. On this feature,
In this right side loading,
yes,
it will give rolling moment about the balance axis
yes,
and also pitching moment about the balance center. Balance center will be somewhere in the middle of the balance.
at the right hand setup, you measure rolling moment, pitching moment, and normal force.
N1 and 2.
That's it.
Four
3.
components.
3 only.
Okay, 1 force and 2 moments.
2 moments. That's all. That's the maximum you can. At this installation.
Suppose the rod.
Yes.
The rod you are using now, sir,
Yes.
loading. If you keep it in an inclined plane.
That's what I wanted to suggest you next time. When I was talking to you regarding a new calibration machine, imagine you connecting this kind of rod sting to a robot, and you can manipulate and maneuver to any angle you want in space. So you can have any combination of moments and forces, any combination you want. So this is another way to look at calibration, automatic calibration. I think small places, academic places, can go for it easily, instead of going for huge capability huge systems, but because they don't have the resources for I will do that for probably. He was asking you. You heard what he was asking? Yeah. At this setup, we can only have 3 components. Now, if you incline, you get the 4th one because you have the drag also. Okay. Now, what I'm suggesting is connecting this to kind of robot arm, which can give you any angle you want. In addition, you can also put different weights on these rods, side rods. So the wall also will give you a combination of new moments, all directions. So you can get all 6 components just by a robot. So you can get any number of points, and you can really go up for higher accuracies matrices. Now, for this internal balance, generally speaking, similar to what was done there, again, you read the electrical readout from the gauges for any load that you are exerting. Just that the number of components here is from 2 to 6, only 5 components. You find these components by least square feet. That's the way you are running it. And you get the best coefficients. Least square feet, to remind you, is a procedure to express the difference, the error between what you are measuring and what should come by using your coefficients. And by differentiating the equations, you get enough numbers, enough equations to solve them simultaneously and get the equations. So in least square, the demand is that the error squared will be minimal. Now, the recommendation by the Aeronautical Society, American Aeronautical Society, AIAA, I don't think you are able to, only those who are members, I believe some of your staff is, I don't know if you are a member of AIAA, but who is member of AIAA can connect and retrieve all the standards, procedures and manuals that they have, and one of them is dedicated to balance calibration. It's very interesting, and it's a huge experience of work. So they recommend of 6 by 33 matrices, and you collect them and you calculate them by using this next formula. Again, the procedure is the same. You are measuring one channel and you're applying force to all other channels, also the same channel, but you express the result by combination. Once you take linear, and then the second term is multiplication of two elements. So this way you get matrix of 6 by 33. And again, you solve it by least square. The question is, how do you exert this combination of loads that you want? You want endless combination of loads in order to have enough information to get good accuracy, and that brought us long time back. I was in charge of the development in our place, and we were looking for a job for some of our experts, of our good engineers, and I was asked to find him something to do. I said, nothing too much to look for. We are looking to develop this automatic balance calibration system, because I see these guys who are weightlifting all the time. It's crazy. Once they are lifting and working hard, and then it takes them 2 weeks to analyze the data, because it was linear. So they're crossing graphs, making all kinds of funny things. Third thing, I gave them this this linear regression in 2 components instead of running all this type of graphs. But this is not enough. 2 components is not enough. You have to have all these combinations simultaneously. And the only way you could get all the access simultaneously is by having some machine that will exert these loads. Now, that time I didn't go for this robot. Only these days it's robot are cheap, and I think it's deserved to try it. Those days we were looking for some electromechanical machine that will you connect the balance to the machine, and it will be loaded by kind of hydraulic actuators, and load cells will measure, and so you can you know exactly what are you loading at, and what are you measuring, and you can have as many points as you like in considerable reasonable time. When we started to develop this,
Decide this range of these forces, like suppose say arbitrarily some model is given
yes,
for testing.
yes,
Test for that.
yes.
But how to decide the range for this force?
Good question. Professor asking how to decide the range for the force for the model is going to be tested. This is something the good guy, Michael, didn't know when he was developing the machine. He couldn't know what's good is it. I mean, he was from ground testing, from flight testing. He didn't know what is balance for the wind tunnel. So he was just developing a good machine. Then when we had to sell this machine and explain people what's advantages we get from that, he could do that because he was not from the field. So I had to educate him in that sense. So at first, you take just arbitrary map of loads, just square map of loads. Okay. You say you just have to keep that your loads are within the limits of the balance. In any sense, you shouldn't cross the borders, but you arbitrarily can load them spread. And then you can, let's say, you acquire 1,000 points or 1,500 points, which takes 2 hours, let's say. Exerting the force and retrieving the data, the information, the readouts, like we did it manually. And from that, you get a good calibration coefficients. You can get even what is recommended by the AIAA, 6x96 metrics, and up to 1,900 points these days you can do. So you get one matrix, and you go and you make your testing, and you're happy. What I told the guy, look, you don't understand what you have here. Once you finish your test, you make a histogram of your loads in the wind tunnel. You can retrieve your raw data from the wind tunnel and accumulate all the points you were acquiring and use them as calibration map as an input to the calibration machine. Exactly the points they were in the tunnel. So nothing can be better than that in order to calibrate. When you are calibrating close to the points you are going to measure, your calibration will be the best, right? Resolution will be the best. There's no need to go with rolling moment or drag force to the extreme point if in the tunnel you didn't measure that. You gain resolution if you go only half the way, if the measurements in the tunnel were half the way. You get double the resolution, right? So this is very strong capability that you can just get out from the tunnel, from the testing, take the histogram of the points, feed it to the analyst. I mean, no, you have to make it. You have to work on the balance itself. You have to again take the balance and exert that map of loads that were running in the test and acquire those points by exerting those loads in the machine and calibrate and get a new coefficients. And then you can recalculate your results from the tunnel with the new calibration. I think they haven't done it yet, but everybody here can do it. I mean, there are two machines here in India. One is in NL, and the other one is at Trivandrum. Same machines. We managed to convince them to buy. And this is one lesson I think they can teach. They can show that once, according to your question, you get the best calibration you can if you take this histogram from the test, though it happens after the test. Who cares? You take it from the test and recalibrate the balance and get better calibration matrices, right?
So suppose the maximum load is coming in of say 50 kg, and
Yeah.
my load cell capacity it is say 2000 kg or 5000 kg. Then
That's a problem. That is problem with the test. It's not a problem with the machine. It's a problem with the test because you didn't pick the right balance.
There is one.
that's
Suppose
what like how to decide. Suppose say before testing,
Ah.
I don't know what will be the
That's
load.
part of the good test engineer to get and the aerodynamic group. They are doing the testing. This is what I'm teaching youngsters. That's one of the main issues when you're coming to a test.
We know
Prepare
aerospace
yourself.
dynamic pressure norms, so we can calculate the maximum.
Wait, let me finish what says. Prepare yourself to the test. Be prepared to the values you are going to measure, because once you get your results, you should know if you are in the game or you're out of the game or you're out of it, and not taking results, go home and see that part of your results are cut because you were overloading your things. So this is the first lesson I try to teach the youngsters. Make sure you know what are you going to get in your experiment. Otherwise, you're losing money and time. And when you come there, you see if there is a big error, something is wrong. Either the system or your calculations were something fault. But at least you take care of that. So this is an example of somebody who was not doing his job well. I mean, it could be. It could happen to everybody. Whoever we say, whoever works makes mistakes. Right? So.
Suppose if you have a high capacity balance, suppose some 200 kg.
For us, it's too small.
But your expected load is some 50 kg.
Yes.
So can I calibrate up to 50 kg and
Yes.
use it?
Yes.
It will give.
For sure, it will fine-tune your calibration, just like that, because you are using narrow range of calibration. Imagine you have this ruler here. It's the same like this. You have a ruler with now division of each one of millimeters, right? And you say, oh no, I need only. You have it on the rulers. You see, in 5 centimeters, you may have half a millimeter also division. So you get better resolution. You have more points. Once you are decreasing your range, of course, you'll get better resolution. But one thing this machine cannot do is making your balance better. We discussed it. I mean, if your balance is wrong and they are not gluing well, that the points of strain gauges are not located well, stiffness is not calculated, the connection is not well, this machine cannot. The accuracy of the machine is very much depending on the quality of balance you're giving them. It's not by standing by itself. By itself, I can say that such a machine
Sir, in the previous slide, the 25 elements linear matrix 0.1%.
Yeah.
Suppose if I go by 6 by 96 matrix, can I get accuracy better than this? Or 25, maybe this is 5 by 5 matrix. For that matrix, we have an accuracy of 0.1%.
yes,
Suppose if
of
I-
course, you'll get better. No question. This is only report, I believe, by one of the first team that bought this machine, 97. I think this is No, this is another. No, this is some other one. I don't know. No, this is very simple calibration. This is somebody else. This is not the ABCS. I'm saying this is an example. Somebody was making his calibration, but it can be much better. This machine was first introduced to Microcraft, a company in San Diego. I was still then, and I was very happy about the results, and I was really keen to have NASA buying this, and they were doing a hell of benchmarking on this, and they found it very accurate. The chief of the testing group in AIAA is the same guy. It's Dr. Cahill, David Cahill. He was making good results, but still we didn't manage to convince him. But Microcraft company in San Diego, they bought it. 97, it's already 20 years. Microcraft. You no need to write down, because they've changed the names 3 times since then. Now it's Triumph. Now, the moment they bought it, they started to calibrate all over, including NASA. So they are calibrating center. Now they are calibrating center annually. They are publishing a paper about the machine. This upgrade, that change, that change, that change. I was a bit embarrassed. I was a bit upset, since I was following the papers, and until recently I didn't see any word about us. Always I saw ABCS, and this is one of the best machines. There are only 2 like this in the US. So I told Michael, next time you are there, tell them we deserve to have some connection to that machine. So in 2013, I see it was not done deliberately, because they were mentioning ABCS, and everybody knew in the community. Everybody knew that ABCS is II machine. But still you would like to get some recognition, and I see a paper in 2013 that it is fully dedicated, the abstract there, dedicated to Michael, saying Michael was developing, and II and this and that. Not everybody who was involved there got the credit, but at least one got it. Anyway, we'll get back to that. So, as I...
Here I have one point. This loading points previous 1000 to 1900. So the accuracy will improve if we do the loading points more than this 1900.
I don't feel so. I don't feel so. The more accuracy you gain is by retro calibration, as I was describing into the answer to the professor.
Okay.
You see, on the left, you see the initial calibration range, and after the test, imagine that the blue area is your histogram of the testing. So you take those points, refeed the machine with the balance, and recalibrate. That will give you much better results.
Even that, if I have more loading points, can I get still within that histogram only range?
It's not significant. The most significant here that you are intuitively, the most significant issue is that you are reducing your range. Once your range is high, that's more important.
To this range only.
Yes.
But even in that range, if I have more points, will I get?
You can use any number of points you like. You can use any number of, because then it's then instead of 2 hours, it'll take you to 4 hours. No problem. That's not the issue.
What does it mean when it says 3rd order matrix?
It means the further combinations of loads. This one. it has the earlier matrix was only two terms of loads, and the third order is including also loads on the third order. That's it. That's what it's saying. Sometimes they are sensitive. I think this is a bit exaggeration.
You're saying they're not linear or
Yeah, this is a bit exaggeration. I mean, not to go so far. But if the system gives, you can do it. But I'm sure second order will be sufficient, and sometimes for our purposes, even linear will be, or first order will be much also enough. But if you get it, you do it. So I took those photos from the brochure of that company, Triumph, and just to tell you, I mean, I don't know if I can expand this. What I just milestone of such a machine. We started development in 1988. We thought it will take us 2 years, but it took more than that. And then after 5 years, we went and presented the results at the Supersonic Tunnel Association. Michael still didn't know what to present there because he was still the electromechanical guy developing the machine, but he couldn't know exactly what is the relation between the machine and the wind tunnel. So I took the lead there to present the results in the STA 1993. 1997, Microcraft bought it. And since then, I think there is machine in Singapore, in South Korea, 2 machines here, one in the States, and of course back there. I believe there are many systems like this in Europe, but wherever you ask, especially these guys waving the machine in US, it's uncomputable. It's unbeatable. When you have the money, it's worthwhile. I don't see any academic institution buying such a machine. It's a bit expensive. That's why I'm suggesting for us to develop the robot system. I think I stole some time. Maybe we'll wait. What is it? What time is the? What time is? Are we breaking now? Yeah, we can break now. We can break now.
The slide, can I see?
Which one? It's not my control.
This is 1997 and 2016.
No, the name. I mean, they are called now Triumph. Microcraft became finally to Triumph. Now I don't know when exactly it happened, but
The ABCS was they have taken ABCS in 1997.
exactly. They were making a lot of changes, upgrades. And if you want to know, I don't know if we can quote figures of how much it costed. I just talk about multiplications. The price they paid, the price they paid, I think it was not too much, not more than 50% increased in 2001 to NAL, and it was another 50% increased once it was sold to South Korea and Singapore, I believe, and another 30% to Trivandrum. But things have changed. I mean, the system also improved a lot. There's no issue. Depends how much you need it, how much you're going to use it. Especially when you are dealing with axisymmetric models. it's very sensitive. You need accurate numbers. But the final uncertainty is something we have to discuss in another session. Maybe we'll open up some discussion about the final accuracies of the measurements. I was not planning to give it. It's a special course I give in second year at my place. I don't think they give it in the university. It's a fact they're asking me what to do. And you are already grown up, right? You are already several years after graduation, right? They are not giving it in the university. They just give you go test A, B, C, D, measure, calculate how much is the uncertainty times square, take a square root and go home and finish with the report. That's it. So it's a bit frustrating. You have to be more aware of what you're doing. I don't want to talk about it here. We'll talk about it. I will talk about it. Maybe fourth day when I'm talking about systems, about measurement systems. It's not yet in the material. I have to work on it still. I lost it, and before I left, my drive memory crashed. So I'll probably dedicate some time for the accuracy of measurements. How you get over that. So let's have a break. Any question?
These balance systems, how do you decide, like in terms of when you have a bigger wind tunnel or you have a smaller wind tunnel, or the speed in which you are operating? Like in the transonic wind tunnels, you have a string system. So
you have to ask louder. I don't follow you.
I'm saying that these balance systems, based on the wind tunnel size, how do you decide which one is the required wind tunnel?
You have to know. Excuse me. Question is if I know how to decide what type of sting balance to use, the range.
Yeah.
So this information should come from the customers, the aerodynamic department that is ordering the experiment. They should, part of preparation for the experiment, for the testing, and it not only for the balance, but it should be a standard procedure. They come and they want to test this model. Take it and test it. No, you should give me all the expected loads on all conditions and all expected results on the scope of testing. Because once I'm running, the wind tunnel is running, there are endless options for snakes in the wind tunnel. There are a lot of options. There are so many components. Every time any component can mislead. And if you don't see it on your data run by run and see everything is correct, you may come out with a series of results which irrelevant. And I saw experienced guys are being mistaken in that. I recently met some guys who are making experiments for 1 week or 2 weeks. You cannot imagine how much it costs. And after 2 years, they're going to analyze the data. What shall they do? I mean, even the guys who were testing, they are not yet anymore there. So whom they ask if they see some CL Max funny result? What shall they do? That's a waste.
I was also asking in terms of if you have a smaller wind tunnel, then
Same.
dynamic institution, and then you cannot accommodate like a sting balance in there or something like that.
Okay. What I did, I bought 2 components only at the moment. For 30 centimeters anyway, I'm not going to run their anti-ballistic missile, anti-ballistic air missile. I'm going to buy to test their 2-dimensional profiles, or even aircraft configuration, but nothing to do with fancy things. I just want to check with just preliminary trends. So that's enough if you use semi-model attached to the load cell on the wall, and even 2 components, CLCD, and you get basic results. You don't need 6 components for this kind of job. And if you work on a profile, airfoil, same.
If airfoil is running end to end on two sides, the two-dimensional.
Yeah, you must have both sides. If you want to measure, you need both sides, unless it won't vibrate. It can vibrate. You need both sides to have measurements. Another mistake my young guy was doing is he thought he can hold the other side and measure correctly, but it's funny. No. If you hold the other side, the strain gauge will not read the right readings. It must be free, floating. So he said, no, I divided by 2. Who cares? Who says? How do you know it's 2? So these are lessons of youngsters. Of me too, because I need to know where can I lose them. Anything else? Actually, we finished with the balance issue at the moment. If you want to go, let's go for the break and then come in. If you have some new additional questions, I'll take them. We'll discuss. I'm sure I've not covered everything. Maybe I'll address your questions without addressing you, because I don't want anybody to. It's being broadcast to all the world. I don't want anybody to fall on you. I just talk generally. Okay, we'll have a break. but um, I don't know what happens here. Fourth-year students are searching for companies to work
Yeah,
at.
that's what happened here. Yeah.
Also,
Yeah, yeah, yeah.
and this year one of the students introduced me to a company which was looking for something to explore in the wind tunnel. So I got one job from them. So it's combination. I'm not going and selling the services, but there is a lot of.
So there are companies building wind tunnel basically. They're maybe working with the tunnel. I thought because it'd be Air Force only or
You mean where? In US?
in Israel or
Nobody is building wind
Doesn't use, I
tunnels.
think there's an Aerolabs.
It's not. It's not in Israel. It's
No,
not
no,
in
Aerolab is I think a British company or US company. I'm not
US.
sure. US company, right?
You ask them how much they charge.
Yeah, they probably charge a lot, sir, because I went through, I saw some of their, they have probably built a build to big ones also. They have shown some pictures.
See, we built a fluid mechanics laboratory. It was not me, it was my predecessor. He had to build very fast the laboratory. Yeah, because I'm ready to take some questions if you like for regarding the balance calibration. One lesson, important lesson, is that people realize that it's impossible to get accurate results without automatic calibration. It's unimaginable to load balance many axes simultaneously. That number of loads, it's actually impossible, and it won't be accurate if you make it manually. People are tired and they don't remember what they are doing. It's useless. So it's impossible to think of something calibrating seriously without the automatic calibrations. That's the lesson. And every serious wind tunnel, commercial, they will have their own. If not using central place to calibrate, they'll use their own semi-system that they will develop. So this is the way it is done.
Sir, how are you expressing the accuracy of balance calibration?
We are talking about how do you specify accuracy of balance calibration. Formally, we are using the same definition in any other calibration accuracy. Formally, the demand was of 0.5% full scale. Today, it's decreasing to 0.1%, and I believe people will not commit better than that, because
The manual calibration rig also, same order?
we were claiming then to 0.5%, but I doubt if it was really 0.5%. But that was the figure that was quoted, 0.5% full scale, which is not so good, because if you're looking about full scale, if your balance is 1,000 kgs, 0.5% is 5 kgs. 5 kgs. If your model is a bit low, small, then it may be a problem.
Do they have to be calibrated often? Like,
Tell me?
do they have to be calibrated often?
No. Usually, string balances are not calibrated often. But with this automatic machine, you would like to calibrate retro. I mean, if you have a set or series of experiment, then you probably would like to gain some more accuracy, so you retro calibrate your data according to your histogram of the test. So
I was talking in the hysteresis sense. If you have one set of measurements done, and
I hope you are not confusing histogram with
no.
with hysteresis.
No,
Okay.
Yeah.
And with history. What is your question?
I'm saying for hysteresis effects from the string, if you have some.
This is the reason why you cannot commit in such system to be more accurate than what it says now, one tenth, because it's dependable on the balance that you are calibrating. If you are given to calibrate the balance, you don't know where it was produced, how much accurate it, what's the age of that system, and it can be very problematic. So it's reasonable to talk about 0.1, but it should be carefully checked what kind of balance you are calibrating, if the balance itself is reliable. We had a lot of troubles with balances that were not reliable, so calibration could be also. And this is one of the reasons the system had this very long time of let's say learning curve. It had a very long time of learning curve, because it was interacting and get reliability upon balances that you were given, and if balance is not reacting well, then it is disturbing your your results. You don't know if it's coming from the calibration machine or from the balance. So that's
If
it.
you want to build like a simple automatic calibrator, for example, like
That's what I'm proposing you. Propose it to your professors, and I will come and will make this kind of. But you don't have a balance. You want a balance. I intend.
I'm considering for this string, this thing, 6-component string balance. That's why wire balance with strain gauges. So that is why we had not got out of that.
I don't know.
And plus, the wind tunnel has to build first before we.
First of all, you make sure that you build your own strain gauges. You build your own components, stress components, because otherwise it's very expensive. I mean, it's not the strain gauge themselves, but the measuring elements. You better train yourself and build them yourself, because it's very expensive, and you will not get the budget. And it's not so complicated, really. Those strain gauge manufacturers, they'll be very keen to sell you all the materials so you can handle it and you work it out. So it's a good exercise to start with. 1 component, 2 components, and build your own system. It's not expensive. Think of it. If you have to do it yourself, 1 strain gauge is not so expensive, and the only thing you have to calculate your flexure. You have to have a good gluing material which you get from the manufacturer, and you start exercise yourself. Look, we'll talk about instrumentation last day. I'll give my example. When I was doing my PhD, I'll repeat it and I'll show you, so it will be shorter then.
Excuse me, sir.
Uh-huh.
What is gauge factor? What is significance of it, sir? Gauge factor.
What?
In a strain gauge, what is gauge factor?
Yeah, it is the relation between. We'll talk about it on instrumentation. Instrumentation, we'll talk about it. It's the sensitivity of the electrical response to elongation, mechanical elongation. So when you design your element, you have to take in consideration what is your response, the electrical response of this gauge. And according to that, you have to calculate your stiffness of your element that you want to stiff on, to see what deflections you'll have. So this is connecting between the loads.
Electrical output.
Yes. Yes.
Excuse me, can you throw some light on floating balances to integral balances?
Actually, we didn't have any experience on that. You mean two part balance, or two part balance to?
That integral balance is our strain gauge balance.
Floating frame balance.
Floating frame balance will be there, sir. There will be no interaction.
Able balances. That is the floating.
We have no. I don't have any hands-on experience on that. I wouldn't like to. I just know that the cost of these elements are very expensive anywhere, because the number of people are dealing with it is they are disappearing. I mean, you don't see any more people working on that. This is something I was starting to tell. As a student, if you plan to work on some system, you better work it yourself, because you'll be unique. You will be demanded on your subject. When I was doing my PhD on mainly on with hot wires, and even today, I look at Dantec, Swedish company that is producing the systems, and when you look at their hot wires selection, they are very limited. I was sitting there in the lab. I will not tell you how much I was cursing that time, but now I'm proud of it. Building a rake of 10 normal wires that could measure simultaneously in the bound layer. I'll talk about it. So then it was hell. Imagine to weld 10 normal wires under the microscope and this and that. But and everybody were escaping from that. My friends, just you didn't see them. They were calling the technician to weld the normal wire because they didn't like their job. But I felt, in order to be capable of doing the experiment and see what I'm doing, I should do it myself. And this you don't see it. I don't see it anywhere such kind of probes, even now. Only, you know what? A friend of mine in Princeton, they are doing they are doing nano probes. I think they are getting better. They are getting better. They are producing the technology of MEMS, micro electromechanical system production. They are printing many parallel micro probes, and they are doing a very hell of a job, I think, on that sense. But you have to start with something.
Yes, sir, one question I have.
One question.
Can we identify turbulent boundary layer or laminar boundary layer by some measurements, sir?
Better we'll speak about it on last day. Last day I intend to, I'm still working on it because I lost the material before I came. I'll give collection of measurements and visualization technologies, and also in the first part. And the second part I will talk about special measurements. So for sure I will elaborate on things that I was celebrating when I was a bit younger. Still, this is again. I'm surprised to see that nothing. I mean, see, everybody even these days referring to what is done at NASA 1950, 1960. Some things remain the same. I mean, fluid mechanics has not changed. Nothing. Viscosity is there. Turbulence is there. Nothing has changed. Only technology has improved. It's like in the Olympic Games. People are not running faster. Only the measurement system becoming more accurate, and you get more numbers behind the point. But people are not running significantly faster. The whole issue since 1960 is 0.4 of a second. So what's the deal? The same there. I mean, if you look back and you see what people do now, and some people are really not looking enough what they've done in the past, because they're losing time, because a lot of things has done. You better look and read what has been done and try to be innovative, not to repeat what is done. It's a waste. But having your own capability to build your own system, parts of the system is an advantage. Big advantage.
Any precautions while starting up a low speed wind tunnel?
I believe I'll talk about it when we discuss high speed wind tunnel. The next subject is high speed. We'll take care of that. We'll talk about it. So you brought me to the subject. If we don't have, I mean, we'll have, of course, endless subjects to discuss. If you will go on and start the high speed issue. We still have some time. Let me see. Intermittent is simpler to design and less costly. Also, you can use a single drive, one power station to many facilities. You can dedicate it. Usually, you can use it for the transonic, supersonic, and also for the hypersonic if it's a separate machine. That's what happens in most of the places. You just pump the storage tanks and then you can use it wherever you need. So that's an advantage. The access to the model is better because usually it's open. You open the test section, access is easy, and in the closed circuit usually you have like a submarine, and failure of the model is damaging the closed circuit. It will not harm the intermittent blowdown. And always you have extra power to start the tunnel, or you can reduce and start the tunnel with lower back pressure, where in the closed circuit it's only one route. You start accelerating the fan and you will get your starting load at whatever you have. So unless you are doing some procedure that will cost you a lot. I mean, starting with low pressure and then increase. And coming to the starting and stopping loads, they are moving faster. I mean, once you accelerate in closed circuit, acceleration is there and it's mechanical. So it should be slower than blowdown.
So can we not avoid starting loads, stopping loads?
We'll talk about it.
Proper design.
We'll talk about it. Just shoot back to you on this thing. Starting and stopping loads, they are there when you start the tunnel and the shockwave is running through the test section, and vice versa. When the air is closing, because Mach number is decreased, the shockwave is coming back through the test section. And once it's going through the test section, it goes through the model, and you cannot guarantee it will go this way, it can go any way. And once it is inclined, you get all this pressure difference between across the shockwave, and you get all this as a power, as a force. So shortly, one way to decrease the pressure jump across the normal shock is to reduce back pressure to minimum. Because if your back pressure is very low, you get a high Mach number even with low total pressure. So that's the way we do it. I know NAL is talking about this for long, but I don't see they are doing something. I don't know. I didn't hear.
They have some plans.
I know. I was visiting them. I was trying to suggest to help, but I don't think they are moving.
In the continuous tunnel, we cannot change the Reynolds number, P naught.
You can, if you have this compressor, additional compressor, you can increase the pressure. The in-draft tunnel is advantages upon blowdown, simple blowdown. Once, I mean, you entrain the once you entrain the air from the atmosphere, then your total pressure and total conditions are constant. No issue, no question. The only weakness here is that you are unable to have higher Reynolds numbers, higher stagnation conditions, because you use natural standard conditions. So this is the disadvantage. Anyway, the advantage we said. And you don't have to use pressure regulations because you don't have any, because your pressure is constant. You use pressure regulator when your pressure is changed along the testing. Yet you may need to do that before the vacuum chamber if it's not big enough, because
in this endraft tunnel,
yes.
is there any limitation of getting Mach number? Can we get any range of Mach number in this?
Theoretically, yes. Theoretically, yes. If you can
pressure
get
ratio.
Yeah.
Our upstream is only atmospheric pressure.
No problem.
But, the vacuum side.
You can get any low number you want. Theoretically.
Theoretical.
Yeah. The only point is that Reynolds number will be not so high.
Very low.
Yeah.
So,
Yes.
so on the previous slides, sir.
Tell me.
On the previous slides,
Previous slides.
the one before this, sir.
Sorry.
We use a divergent duct for a diffuser, sir. In hypersonic case, that doesn't act as a diffuser, right? It's only a convergent duct that acts as a diffuser for hypersonic conditions, for high speed conditions.
Please repeat your question.
So for high speed conditions,
Yes.
it is a convergent duct that acts as a diffuser.
Here what he says is supersonic diffuser.
Yes.
And here also there is a supersonic diffuser followed by subsonic diffuser.
Okay.
The diffuser means it is two parts.
Wha-
After the nozzle, you see, there is one converging.
What is the question? What is the question?
For supersonic conditions, sir,
Yes.
it is a convergent duct that acts as a diffuser. But here I see only a divergent duct that acting as a diffuser.
No, there is a converging, you see, after the nozzle there is a converging duct. The second throat is there.
Nozzle is here, and behind it you have a second throat.
That is a converging.
So what is the question?
So,
You got it wrong? Okay. Okay. Great. So where are we? Oh no, we are here. Back and forth. Okay. Vacuum is simpler to handle because it's low pressure. When you have high pressure, you have a risk of.
I have one point.
Yes.
See, the spheres generally, large spheres, vacuum, why can't they be cylindrical? Why they are spherical? Large size if you take.
Why asking me? You've been to Trivandrum. Ask them. Huh?
We are the master.
No, I think. Yeah. I think the loads. Since you are very close, the loads on sphere will be less. The loads on the sphere will be less.
Yes.
Since you are in vacuum, you calculate and see what is the load on the metal for cylinder and sphere. You see it's much less.
Stresses will be.
Yeah. Yeah.
Yeah.
Noise in this indraft will be lower. And lower cost of construction because vacuum pump is cheaper than pressuring pump, but usually you have pumps also on the other side. You don't use the free air, so this type of saving is not practically there. But if it's only suction concept, then it will be cheaper. You don't need a big compressor. You can have a vacuum compressor, which is much less cost.
Diaphragms are generally used, like, what's the specific purpose for it?
For?
Diaphragms, before that test section, like after this valve, people they are using diaphragms, like aluminum diaphragm.
Who? Who is using?
For this kind of tunnels, I have seen people they are using diaphragms. So once they open this valve, the diaphragm that
I think you're talking about shock tunnel. Where did you see it? Where did you see it? Where did you see it? Where?
in Bombay.
It's a shock tunnel. We'll talk about it.
So for a comparable in-draft versus blow-down tunnel, which one will have a lesser pumping time, pumping versus vacuum?
Pumping time is a function of the compressor you have. If you, let me say this, if you had the same power you need to press for evacuating, it will be much faster. It's easier to vacuum.
Okay, power is also power consumption is also.
Of course. Yeah. Okay, what are the advantages of blowdown? It is possible to obtain different Reynolds numbers. Cost of construction is significantly less, construction-wise, because you have less components. This sphere all around it, it's a big, it's very nice, impressive, but it's cost-wise. And the time of test it can be shorter until the stabilization. It's shorter. And I think we discussed this. I don't remember why, but anyway, free drop tests, jettison tests are capable of blowdown, but in draft, you'll have to look for the elements. Then in the sphere, you'll have a journey there. You'll enjoy your time looking for those. Next. Some phenomena in high speed. We'll talk about some theory and see how it comes to reality in experiments. Those of you who didn't take a fluid mechanics compressible flow course, it's here. Who took the course? It's good to remember. Sometimes there are myths and not everybody is covering this. I don't know how many times you heard this supersonic boom when an aircraft is crossing over your head. Sonic boom. People usually tend to think that it is one event. Why do you saying this?
It will like
Continue
What?
vibrations will
like shattering.
No, but you are standing here. I mean, once aircraft is crossing Mach number 1 and you are standing below, you hear one boom and that's it. You hear one boom. Actually, I have a nice demonstration for what happens here. I'm not sure. Let me see. I think I have something. Yeah, it's the next. So anyway, what happens is any air vehicle or anybody that is moving in the air, it will create disturbance, acoustic disturbance, and as long as it is moving below speed of sound, the disturbance will disperse, nothing happens, everything nice, like you throw a stone in the water and you see these nice circles coming out. Once the element is flying close to the sound, the speed of sound, it presses, almost overtaking the front of the disturbance, and it builds up a front of higher pressure in the front and lower pressure in the back. Once the element is flying faster than speed of sound, then every time is overtaking the front of the disturbance it was creating, and this way you get front of pressure, high pressure, in the shape of the tangent to those circles of expansion of pressure. We miss here the event where the element is flying at Mach 1, at the speed of sound. There is a vertical line which is converging all the fronts at once, because any disturbance it creates, it immediately stands with the front. So you have a vertical front, and this is the strongest pressure jump you can feel when such an aircraft is flying over you, when it is crossing Mach number 1. But then, when it's flying at higher Mach number, you get this front of pressure axis, and geometrically you can express the front as a sine of 1 over Mach number. It's simple geometry, and you see the cone, including the half including angle. It's a function of Mach number. So once you are sitting and you hear the boom, you see the aircraft, you can imagine, you can calculate what Mach number it is flying by guessing what is the angle. I'll show you these nice videos. I don't know if you happen to see them. Of the next. Why we are not moving? Okay. See. This is a well-known photo. You see it here and there. I use it also at the front of one of my books, class notes. You see F-14 flying in some place in the coast. So he was flying through a cloud, and immediately the cloud was setting himself around the Mach cone. Let you see it how it happens. It's a very nice thing. I must hear the voice. Tell them I need a voice. No, it's nothing to do. Can you tell them? I need the sound. I need the audio. It's useless to show it without the audio. Maybe they close the shop now, no? No? Is it operating? Okay. Let's check it again. No. No, you see it. You see that cone. So I want to have the audio. Meanwhile, we'll see what happens. So if you take and just measure, you see the angle is 53 degrees about, and 1 over 1 sine of this. To get Mach number, you get this so you can know in what Mach number it was flying there. Maybe you go home and tomorrow we'll have it. It's already out, end of the day. You think he'll solve it, or just he said he'll solve it? You just he said he'll look at it, but he didn't say when.
Mu 53 degrees, how did you get that is angle between?
How do we get the 53 degree? The 50 degree, I was just drawing it. I was drawing a line which is coincide with the cone. Shall I check?
Yeah.
Or I kick it harder? What are you suggesting?
No, just say this
Okay.
one.
Okay, wait just a second. No. No, it doesn't show any.
So you have any other audio? Just check it.
Any other movie?
Yeah.
Okay. Try the other one. Now don't tell me it's the same aircraft, because it's not the same movie. Okay. Let me continue. See, if the aircraft is build up on this airplane. Look at that! Oh yeah! Only when it passes and the boom is crossing, there's this noise. Now it's silent.
Ladies and gentlemen, the Super Hornet high-speed pass.
Ladies and gentlemen, the Super Hornet high-speed pass.
When
This is the direct camera, sir, or some special glow visualization?
no, simple one. You see it in simple eye. So if you are in front of this wave, you don't hear anything. You don't hear the aircraft because it's flying more than the speed of sound. So the sound is not reaching you. Only after this shock wave is passing you, you are in a region where the disturbance is able to expand. So this is we're starting with this on the principles of high-speed supersonic, and next tomorrow we'll talk about more. So let's go home. Enjoy your evening.